So, basically ABCD matrix that we know. So, what we have seen is that actually theta L phi L can be written in terms of theta 0 phi 0, something like this we can write it. Now, this boundary condition, two of them must be known to find out the other two. I can treat them in different manner. I said that one of the ways is doing it in frequency domain, but if I do it in time domain treatment, which we are not doing in this class in details, but I will explain you what it is, because American Society of Heating Refrigeration Engineers, good old days, now the computational capability is too large. But earlier days when even you had, you see this kind of ideas, this came from I think Milbank, frequency domain came from Milbank and Harrington Lin, and I think time domain came from mostly from United States. I am not remembering the gentleman's name. Now, they used a different kind of treatment. The treatment was something of this kind. Any function if you look at it, say temperature versus time, and if it is something of this kind, you can actually approximate it by pulses. Take delta t, delta time, this is the delta space time, and small delta time, and you can break it into rectangular pulses, approximated by rectangular pulses, right. And better would be if you take triangular pulse. Better would be if you take triangular pulse. For example, this is this is 2 delta and this is a triangle, then there is another 2 delta triangle. So, actually there is a superposition of 2 of this, and it actually fits better. You can see it goes very close, where this is something like this. This one triangle, if you sum it up, this 2 triangle, this triangle, one triangle like this, twice of this triangle, it fits fairly close to the actual curve. There are other kind of transformations available for this sort of situation. So, what I do is I find out the response to single pulse, response to unit temperature pulse, single unit pulse. So, this is unity, let us say, and response to this unit pulse I find out, and there will be train of such pulses. This is one, followed by this train, it is a complete number of such pulses would be there in actually a 24-hourly temperature profile. There will be a number of such pulses, and unit pulse if I find out, multiplied by this value, that will be the response due to this pulse. A time which has come delta time earlier will be, two things will happen. This will have a pulse response of this one will not be instantaneous. I mean, response will be something like this. Let me see if I have the, response will be something like this. For a triangular pulse, for example, unit triangular pulse, I will have response like this, and response will continue for quite some time. Then it will die down gradually. If I have a unit triangular pulse, if I can get a solution of this one, assuming my boundary condition that there is a unit triangular pulse of temperature, let us say, or heat flux, whichever I want, maybe temperature. So, I give a unit triangular pulse, and response to this I can find out over the period of time. Now, I would have another triangle before that, and there is another triangle before that. So, this one, response of this one, let us say I am interested in this time, response of this one will be this much, response of this one actually will be this much, because it is delta time earlier, right, and response of the previous one will be this much. Do you get this point? Response, so since there are trains of pulses, there are several pulses, this is the last current pulse I know, and there are many pulses before. And let us say I take unit, but multiplied by the actual amplitude or actual height, because it is a linear system. So, like I was showing you here, this is unit pulse. If I multiply this response by this value, then I get the effect of this pulse at this point of time. This pulse, its effect I can find out at same point of time, because it would have come 1 delta earlier. So, I can sum them up, series of them I can sum them up, and triangular pulses, there are better ones, as I said. This is the basic philosophy behind it. I am not solving them, because that is not amenable to hand calculation easily. Escher had tables available in their book earlier. Now, of course, many, I mean the programs are available. I believe that early DOE, 2 program in Fortran 4 might have been based on that, I am not sure. But there are modern ones, many of those softwares which are available are based on finite element or finite differences, because better numerical methods are available, but it really does not make difference. I will do that one which is amenable to hand calculation or Excel spreadsheet, simple, so that you understand the thing. Software you can easily use, and if you know what is inside, how to give the boundary conditions and how to give your inputs, that is good enough. But basic principle is something like this. So, time domain treatment is done in this manner, as it is said, temperature or flux, unit change in rectangular excitation, heat flux to unit response function that is known to us, and then any response for a temperature, it will be sum of m equals to 0 to infinity. That means infinite number of pulses starting from the current pulse to the previous pulse, m delta, right, m delta, because each one is delta, and its excitation is E t minus m delta. So, actual multiplied by the excitation, I mean as I was just telling you. So, this I am calling as E, this is E, E excitation. So, excitation current one will be current one will be m equals to 0, current is t. So, m equals to 0, and then m equals to 1 delta time earlier, excitation value E, and the response also earlier time. So, you sum it up, the response of the system you can obtain for any construction you can obtain, and store them, keep them recorded for your purpose for future uses. That is what was done. RT is the system response at time equals to m delta. These are response factors, is response factors at time a delta. This is the excitation at time t minus m delta. So, this is the time domain solutions. Time domain solution, the principle is this, and you can actually use this. Now, the the solution to temperature, this must be known to you, and this you solve that ABCD matrix solution. ABCD is related to the section, and it is a function of S. ABCD is this matrix coefficients, they were they are essentially function of they have section and S, right. So, there will be function of S. If you when you for the pulse for a unit pulse, the boundary condition now theta 0 is unit pulse, you take Laplace transformation of triangular pulse and k into S by R, or Kp Laplace transformation of first derivative of temperature dt dx, that will be phi. So, that you take, and their responses can be solved. So, problem can be solved, the ABCD is known, you can solve this differential equation and solve values from those, the response values were obtained, and this is tabulated. You can, if you want, you can find out in tables. As I said, we will not solve this, we will not do this, because you have to sum up so many of them. So, it is a relatively cumbersome process, you have to, even if it is stored, summing up has to be done. Well, when computer was not there, it was really cumbersome. Now, it is not that cumbersome, but still we will do simpler one which gives you better understanding. The better one in frequency domain comes when I replace S by I omega. I is a under root minus 1, I is nothing but under root minus 1. So, imaginary, and omega is twice pi f, twice pi f, right, twice pi f. By p we are using twice pi, we are using twice pi by p, twice pi by p, f is 1 by into t, obviously. I mean omega, I am saying omega will be time period. So, capital T in many other places you have used, we used earlier p. So, maybe notations are getting capital P I used. So, twice pi by p. So, if I replace this by Laplace transformation, lower limit of integration as minus infinity for first harmonic you can see that all temperature and heat fluxes are multiplied by exponent e to the power I. Let us see how we do it. Let us see how we do it. See, if I am doing it, let's do it for cos hyperbolic, what was it, under root s by alpha, and it was L or whatever it is, that is right, that was it. Now, S I am writing cos hyperbolic I omega by alpha L, right, that is what it would be. And Laplace transformation would be what, of temperature would be e to the power minus s t, t as a function of t dt, and this was from 0 to infinity. Well, this is I can use minus infinity here, minus infinity to 0, the function is 0, right. So, I can use like this, and what is e to the power s t minus s t, s I am replacing by, so minus infinity to plus infinity I omega t dt dt. What is e to the power I omega t? This will change like this, and temperature, Laplace transform of temperature will become something like this. So, what is e to the power I omega t? What is e to the power I omega t? E to the power I omega t is cos trigonometric function cos omega t plus I, right. Now, if I multiply by cos omega t this function, what do I get? Can you recollect? If I multiply this t by cos omega t or sin omega t, I get Fourier's coefficient. How did I obtain Fourier coefficient? By multiplying this one, recollect this Fourier coefficient a, j, b, j, etc., etc. I multiplied this by cos omega t, I get the coefficient of cos. If I multiply by sine, then I get the coefficient of sine, which are b, a, j and b, j. So, you can see that this becomes actually nothing but, this becomes nothing but Fourier's coefficient, simply Fourier's coefficient, a, j, b, j, this is nothing but Fourier's coefficient. In other words, we will just see this, in other words, we will see this, sorry, you will see this, all temperature heat fluxes are, then I will have a term multiplied by e to the power I omega t integrated from this to obtain the transform. So, you will have something like this, e to the power I omega 1 first harmonic t t is nothing but t t cos omega t dt, because this is cos omega t, this is cos, I have multiplied by this. So, cos omega t dt sin omega t dt, this is what it is. So, this is nothing but a 1 a j. So, this 1 I have taken only the first harmonic a 1 minus I b 1, right, and a pi term will come, pi term will come after integration actually, because this was, remember it was pi by 2, remember it was pi by 2, and now I am integrating from minus infinity to infinity. So, a pi term comes, remember that it was a j was pi by 2, I have to divide therefore a 1 by, like it was pi, there was a pi involved in that equation, if you remember. I multiplied by cos omega t t t, and a j is nothing but this integration divided by 2 by pi, remember that. So, a j multiplied by pi will come a, and then integrating it full. So, pi a 1 minus I b 1, that is what it comes. So, this is nothing but b 1 is, this one is nothing but same Fourier's coefficient, right. So, I have to now no inverse transform of Laplace transform or anything, simply instead I take e to the power omega t. So, I get something like this, and then this can be written as pi t 0 e to the power I omega t, because if I simply a 1 I can write in terms of t 0 cos omega t and B1 is equals to T0 sin omega t, right. And therefore, if I take square of this, you know, this, if I take square of this, or let me write it like this, earlier one, this one's, so this would be phi a1 I b1, and phi remains. This I expand, what does it come to? Pi T0 e to the power, I mean this becomes cos omega 1 t, cos omega 1 t minus sin omega 1 t, and T0 is common there. So T0 cos omega T0 sin omega t, there will be a phi multiplied, there has to be a phi multiplied, somewhere there has to be a, yeah, t is equals to, okay, I just replacing this a1 square by plus b1 square, right. So T0 is equals to, if I write it in this manner, then this is a complex number which I write it in this manner, then T0 will be a1 square plus b1 square, you know, a1 square plus b1 square, and omega is tan inverse of b1 by minus b1 by a1, because this a1 I can write as some cos omega 1 t, b1 you write as sin omega 1 t, then a square plus b square is equals to 1. So T0 and e to the power tan inverse of b by a gives me this angle omega 1, tan inverse of, you know, this, if I write it in this manner, tan inverse of b by 1 gives you omega 1. So it actually follows from here, it follows from thus qt thus gets transformed into Fourier's amplitude corresponding to harmonic multiplied by e phi 1 I1 in omega t. So you see, just let us go back to this. This is equals to phi a1 minus I b1, right, and this I can write as phi T0 e to the power minus I omega t, omega 1 t, right. Phi, this I can write as phi E0 I omega 1 t. So basically, if I multiply phi T0 yeah, omega 1 t, that's basically the amplitude, in fact a1 plus b1 square under root will be T0, and phi would be, I mean theta would be whatever it is, the omega 1 would be given by minus tan inverse of b1 by a1. So this, when I multiply, use this term S is equals to I omega, the whole thing gets converted into, my temperature gets converted into phi T0 e to the power I omega t. Similarly, so my temperature, transform temperature, I mean equivalent of theta, it is not theta actually. So if I multiply everything, you know, take I omega, I will get something like this, T0 e to the power minus I omega 1 t phi, and similarly Q0 phi e to the power I omega t, because I have taken, instead of Laplace transformation, I have I did this minus I omega. So when I use this transformation, S equals to I omega, then I get this equals to A, B, C, D, this side also phi TL e to the power minus I omega t, and phi QL e to the power I omega t. Because instead of using S, if I use S I omega, my function gets, after integration, function gets transformed into this. But this I have to change. A was cos hyperbolic under root S by under root S by alpha into L. So S has to be also replaced by I omega, which I will do right now. So does it make sense that if I use I omega, use not only from 0 to infinity, but go from minus infinity to infinity, because minus infinity to 0 the function is, I am assuming it is 0, which I can do, then instead of Laplace transformation, this transformation becomes something like this. That is what I have shown, that this will become, this is nothing but Fourier's A1, and Fourier's A1 can be written in terms of some single function T0, some single temperature T0. So, I will write it in this manner. This transformation can be written in this manner, and you will have T equals to A1 plus B square, where A1 B1 is a Fourier's coefficient, omega 1 represents minus B1 by A1. T qt thus can be transformed to Fourier's amplitude for the corresponding harmonic multiplied by phi e to the power I omega t. So, my equation would look like, transmission matrix will look like TL QL, and here e to the power minus I omega 1 t, here also e to the power minus I omega 1 t phi, here also e to the power minus I omega 1 t, here also phi multiplied by e to the power I omega 1 t. See, everywhere this term is coming. Therefore, it will cancel out, because TL will be equals to M11 into T0, TL e to the power, equation will look like this, phi TL e to the power I omega 1 t is equals to M11 e to the power minus I omega 1 t T0 plus M12, right. So, Q0 phi e to the power minus I omega 1. So, every place this is coming, this will cancel out from all the space, all the places. So, I will be left with only TL QL is equals to M11, M12, M21, M22, T0, Q0, which means that I do not have to actually do the transformation at all. This is simply the amplitude, this is simply the amplitude, this is simply the amplitude, which I can find out from Fourier's sine and cosine ones, coefficients A1 square plus B1 square, that should be under root of that should be equals to T0. So, if you have that Fourier's coefficient which you have found out earlier, we did a tabular form. Same one you can use, take square of each one of them A1 and B1 square, take under root of that, that is this one. Similarly, outside if it is known, then you can take it this way, you can find out how much Q is coming at the inside, or you can also find out how much heat is entering into the system. So, you can actually solve this. Now, only thing remains that expressing this in terms of omega, I omega instead of S. Let us do that. Let us do that. So, is this idea clear? Oh, what is happening? Is this idea clear? Right. So, let me erase everything off. M1 1 2 is equals to, replace S by I omega. Now, under root I is interesting, 1 plus I square is equals to what? 1 minus 1 plus I square plus twice I, right. So, what is this I square? So, right. So, 2I is equals to 1 plus I square. So, 1 plus I square is equals to by 2 is equals to I. So, under root I is nothing but 1 plus I by 1 plus I to the power 2. So, we make use of this and do this exercise. So, all temperatures and heat fluxes are multiplied by exponent phi into e to the power I omega t and can be ignored, but respective omega 1 need to be used in transmission matrix. So, if it is first harmonic, you will use omega 1, if it is second harmonic, then use omega 2 and so on, so forth, so on, so forth, right. So, that is what it is. So, M11 sine, all of them can be therefore written in the same manner, I omega 1, right, and under root I is that same determinant remains same, there is no problem about that. So, under root you can write it like this, 2I to the power half, remember that is what I did, 1 plus I square, right, is equals to 2I. So, 2I to the power half, I just did a little bit of I to the power under root I was there and also under root omega by alpha. So, I just add here 2 alpha, this becomes something like this 2 I to the power half omega plus 2 alpha, right, and then 2 I to the power half is 1 plus I. So, this I call as f, this we call, I mean this is the notation given by people who use it, they use f. So, I thought I will also continue to use the same. So, f is omega divided by 2 alpha to the power half, right. So, under root s by alpha, which we wrote as under root I omega to the power alpha, then turns out to be 1 plus I to the power omega by 2 alpha, which becomes 1 plus I to the power into f, because this I am calling as f, and it can be written as f plus IF, and if you have L multiplied, it will be FL plus IFL and so on. So, that is what we do, that is what we do, that is what we do, that is what we do. So, cos hyperbolic FL plus IFL, because it was cos hyperbolic under root I omega by alpha L. So, this I am calling as, this will become cos hyperbolic 1 plus I into under root omega by 2 alpha into L, and this I am calling as f. So, cos hyperbolic 1 plus I into FL. So, FL plus IFL and so on for others, and that is what it is. So, you can actually find out. So, if you use each individual harmonic, you do not have to go to Laplace transformation or anything, as long as you use single harmonic, right, use a single tone and single sinusoidal or cosinusoidal, does not matter, because there will be only phase angle change 90 degree out of phase. So, you assume a single sine function or cos function, I can simply use this, no solution, nothing is required, and we can, from this we can calculate out the heat coming in or heat going out or whatever it is. So, followed from this M112 and TL QL I can write as ABCD T0 Q0, where let us say 0 stands for outside, Q stands for outside, and accordingly ABCD matrix you find out. Or you can, that is what I am saying, TL is TI QI, T outside, ABCD you can find out, right. Accordingly ABCD you find out. So, let us say take up as an example, because but you must, the basis was important. That is why I gave you the solution to the differential equation, how it has come, although final calculation really does not require all that, right, but understanding, for understanding purpose we must understand this. So, example, let us say simple example, thermal conductivity 1 watt per meter degree centigrade, L is 100 mm, rho is 2000, I have deliberately put it in figures such that you can, H is 15 watt per meter square degree centigrade, C specific is density was 2000, specific is 1000 joules per kg, Hi is 10 watt meter. So, it is a simple problem. So, we want to calculate out the matrix. Now, first of all I must find out FL and FL I should find out, right, FL I should find out. So, we will just break and then solve this problem, right. So, FL plus IFL we will find out, solve this problem, break and solve this problem.